Hi physics students, welcome to part 2 of our motion graphs notes, where we're going to be applying our understanding of motion graphs to solve various problems. So here's the first type of problem you might be given where you're provided with a position versus time graph. It could also be a velocity versus time graph, but then you're asked some questions based off of it. So our first question here is asking about the total distance traveled. The definition of distance is going to be the total ground covered, and so we just want to see how many times does the position change. So if I track it, I see it's changing 1, 2, and then goes back up, 3, 4, 5, stays the same, 6, okay? So the total distance traveled is going to be 6 meters. Goes down 2, between 1 and 2 seconds, goes up 3, which makes it a total of 5 meters between 2 and 3 seconds, and then it goes down 1 position between 6 and 7. Total distance is 6. Displacement is the change in position over time. So basically comparing your initial and final positions. My initial position is at 0 meters and my final position is also at 0 meters. So displacement is going to be 0. And then finally, it's asking about velocity. Where is it positive? So if you remember, the relationship between velocity and a position and time graph is that velocity is the slope of a position versus time graph. Because slope is rise over run, and the rise of a position versus time graph is a change in position. The run is a change in time, because that's the x-axis. So if you put it together, it's going to be a change in position over a change in time as a slope of this type of graph. By definition, that is the velocity. And so velocity is going to be positive when the segment is pointing upward or moving upward over time. And that's what I see over here between 2 and 3 seconds. Okay, here's some more questions about velocity. So it's asking a little bit more specific questions like where's the fastest velocity, the slowest, and where is the object not moving. So to help us out, let's actually solve for the velocity for each segment of this graph. First, we can actually just in general label the velocity as positive or negative for each segment, just based off our understanding of slope. So when your line is pointed downward over time, that's going to be a negative velocity because we're changing position in the negative direction as time is moving on. If the line is pointing upward, that's a positive velocity, as we discussed in a previous slide. If it's not changing over time, there's no change in position, well, that means you're not moving, and so the velocity is 0. And finally, a line pointing down is going to give us a negative velocity because of a negative slope. So that's just in general how to label this, but we can obviously use numbers to calculate the slope for each segment as well. So here are the times, 0 through 7. For each of these times, we can actually track the position using this graph. So at time equal to 0, I notice that position is at 0. For time is equal to 1, it's at -1. For time is equal to 2, we're at -2. Time is equal to 3, we're at +1. 4, we're still at 1, 5 is at 1, 6 is at 1, and then 7, we're back at a position of 0 meters. Using this information, we can calculate slope, which is really just rise or a change in y over run, a change in x. Again, our change in y is going to be a change in position. Our change in x is our change in time, okay? So I'm going to calculate the slope for each segment. Let's start with our first segment right here, which is from 0 seconds to 2 seconds. Because it's really just staying the same. It's a straight line until it changes velocity. So how to calculate this is a change in y. Okay, so our final position is -2. Our initial is 0 over a change in time, 2 minus 0. So my slope for this segment is going to be -1 meters per second. For the second segment, between 2 and 3 seconds, we are changing our position from -2 to 1, okay? That means that my final position is 1, and I'm subtracting my initial position, -2, over the final time minus the initial time. When I calculate that out, that actually gives me +3 meters per second, okay? And then my next segment is this straight segment, this purple segment right here, between 3 and 6 seconds. And the change in position will be the final position, which is 1, minus the initial position, which is also 1, over the change in time, 6 minus 3. So that's 0 meters per second. And then finally, my last segment is this orange segment, which is between 6 and 7 seconds. My final position is 0. My initial position is 1. And I'm dividing that by my change in time, 7 minus 6 seconds. So that's going to give me a slope or a velocity of -1 meters per second. What we can actually do now is we can use this information to draw the velocity versus time graph. So I'm first going to start by labeling my y and x axes with the same values that I have on my position versus time graph, and then and also make sure that it accommodates for the values that I got and for the slope over here, because the slope of a position versus time graph is the velocity. And for each time segment, I'm just going to draw a line at these values, okay? Again, because these values are the velocity, these are the values for my y-axis. For example, from 0 to 2 seconds, okay, so that's the time, I have a constant velocity of -1 meters per second. So I draw a straight horizontal line from 0 to 2 seconds at -1. From 2 to 3 seconds, it's going to be a positive velocity of 3 meters per second, okay? And then from 3 to 6 seconds, it's going to be a constant velocity that's non-existent, so 0 meters per second. And finally, I have a -1 meters per second velocity from 6 to 7 seconds. All right, so that's my velocity graph drawn from my position versus time graph. And now we can answer these questions below. So the fastest velocity in magnitude, meaning the biggest number, I don't care about the sign right now, I just care about the number, is going to be 3 meters per second, and that's happening between 2 and 3 seconds. While in motion, the slowest velocity is going to be, well, while in motion, right? So I can't say 0 meters per second. It's going to be the slowest number. It's going to be -1 meters per second, and it's happening from 0 to 2 seconds, but also from 6 to 7 seconds. Even if this was a +1 meters per second, that would still be the slowest velocity. Again, the negative sign in physics just tells us the direction, okay? The magnitude is by the number. And the object is stationary, which means 0 meters per second velocity from 3 to 6 seconds. How about the acceleration? That's kind of like, that's going to be a challenge question. So using your understanding of acceleration being change in velocity over time, where would we see acceleration here? What would the values for acceleration be for each segment? And hopefully you can answer that. Okay, so now we can try this for another position versus time graph. There's no concrete values given to you in this picture, but using the part 1 of our motion graph notes, you should be able to look at each segment and determine what's happening with the slope and the velocity, and if it's a changing velocity over time or a constant velocity. So for this first segment, I'm going to label right here. It's a constant velocity. How do I know? Because it's a straight diagonal line, which means the change in position is constant. For every second, I'm like moving down 2 units, 2 units, 2 units. It's staying the same as time is passing. It's a negative velocity because it's moving downward. It's a negative slope. And then the acceleration is 0 because it's a constant velocity. How about for this next segment? Okay, so on this next segment, I notice that it's still moving down, but it's moving down slower over time. Okay, so what this means is that we are actually moving down with a negative velocity, but it's moving down slower over time, which means we're slowing down. And that means that it's going to have a positive acceleration, because anytime you're slowing down, your acceleration is the opposite sign from your velocity. Okay, this next segment is a straight line, and that means our position is not changing. So in other words, you have a constant velocity at 0, and if there's no velocity and no change in velocity, that's going to be acceleration is equal to 0 as well. This next segment, I notice that I'm moving in the positive direction, and I'm actually going to be increasing that position change over time. So I see that it's speeding up, okay? And so this is speeding up in the positive direction, so it's a positive velocity. And then we have, since it is speeding up, the acceleration is the same direction as the velocity. And then finally, there's this kind of a straight horizontal segment here in the positive direction. It's a straight line, which tells me it's a constant velocity. It's a constant positive velocity because the line is going up. And since the constant velocity, acceleration is equal to 0. If you take a look here, a big hint that you have a constant velocity is a straight line on a position versus time graph. And a hint that you have any kind of acceleration is when there's a curved line on the position versus time graph, okay? All right, so then if I was to transfer this over to a velocity versus time graph, I encourage you to actually pause this video and see if you can draw it on your own before I reveal the answer. So pause here and then try. Hopefully you've tried, okay? So let's start with our first segment here, a constant negative velocity. And acceleration is equal to 0. So since acceleration is equal to 0, that means on my velocity versus time graph, the slope of this line should be 0, which means it should be a horizontal line. And since it's a negative velocity, it's going to be a line in the negative direction, okay? Over here, we're slowing down. We have a negative velocity, but a positive acceleration, which means my slope of that line should be a positive value. But ultimately, the values are in the negative, I guess, y-axis, which is for velocity here. So that's why these are negative velocity values, but the slope of this line is positive. That's what this is suggesting, okay? This is obviously velocity is equal to 0, acceleration is also 0 because it's a horizontal line. Over here we have speeding up, a positive velocity. As you can see, all these values are in the positive direction, but it is increasing over time. The velocity is increasing over time, suggesting a speeding up. And then this last segment is going to be a constant positive velocity. As you can see, this line is in the positive y-axis for velocity, and it's a horizontal line, which means acceleration is equal to 0. Here is another one. This one I see 3 segments. So here's the first segment, here's the second segment, kind of a straight shot, and then the last segment, okay? Try this on your own. All right, so let's review. So for the first segment, you should have gotten that it's a positive velocity because we are moving up. We're moving the positive direction for the position versus time graph, but it is slowing down. First, we know that there's an acceleration because there is a curve in this line, and also the slope is actually getting not as sharp, right? There's a very strong slope in the beginning and it's slowing down over time. So that means that we have a positive velocity and a negative acceleration. Because we are slowing down, those signs will be opposite. In this next segment, there's still a positive velocity because we are moving up in position, but the acceleration is equal to 0 because it's a straight line, so it's constant. And finally, over here, we have the same slowing down example where it's still positive velocity because ultimately our position is increasing over time, but it's slowing down because that position is increasing less and less as time moves on. So in the beginning, maybe you're moving like up, I don't know, it's not too much. Maybe you're moving up like 1 position, but over here moving up just half and then a quarter of a position, so it's slowing down. So it's gonna be a positive velocity with a negative acceleration. If we draw the velocity versus time graph, I would encourage you to pause and try that on your own. Here's what it should look like, okay? So we're starting with a positive velocity with a negative acceleration. So it's, again, velocity is in the positive part of our graph, but it's going to be a negative slope because slope of velocity versus time graph is acceleration. Then we have a constant velocity that's positive. Okay, so it has to be above this x-axis, okay, in the positive y direction or velocity direction. And then finally, slowing down, velocity moving downward because we are slowing down, our acceleration is going to be negative, okay, but ultimately still a positive velocity. All right, finally, let's summarize our understanding. So with the position versus time graph, the slope represents a change in position over a change in time, which is velocity, okay? A horizontal line on a position versus time graph means there's no motion because our position is not changing. On a velocity versus time graph, the slope is a change in velocity over a change in time, which is the acceleration, and a horizontal line represents a constant velocity because our velocity is not changing over time if it's horizontal. I hope this was helpful. Please use this to help you answer any motion graph questions, and I look forward to seeing you in class. Thank you. Bye.